So what we're going to do is we're going to look at a more complicated example. We're going to look at the polyatomic ion, CO3, 2-, or carbonate, as you guys may know it. And we're going to just follow our steps. First thing we need to do is find our valence electrons. Okay, so carbon and oxygen are the elements that are part of the molecular structure. Carbon has 4 valence electrons, as we figured out last time, and oxygen, if we count over, has a total of 6 valence electrons. So carbon in this molecule, there's only one of them, so we're going to multiply the electrons, valence electrons, by 1, and oxygen we're going to multiply by 3 because we have a subscript of 3. So we have 4 valence electrons coming from carbon and 18 coming from our oxygen. Now, we don't care about the individual atoms, we care about the total molecule, so we're going to sum the total number of electrons that we have coming from each atom. So 18 plus 4 is going to give us 22 electrons. Now, normally that would be the end of our summation of our valence electrons, but because we have a polyatomic ion, because it's an ion, we have to account for the electrons associated with that kind of structure. So because we have a polyatomic ion with a negative charge, we're going to add an electron for every charge. So in this case, the molecule is 2-, so that means I need to add 2 electrons. Okay, so that's going to give us a total of 24 electrons for our molecule. So now we can proceed on and start working on the other steps. So just like the last time, step number 2 is going to tell us to put the least electronegative element in the middle, and in this case carbon is the least electronegative element because it's farther to the left than oxygen. Okay, and then oxygen subsequently surround that least electronegative element. We then move on to step number 3, and we bond each of our central elements, our central element to each of the exterior elements. So I've used 3 bonds. Each bond has 2 electrons. That's a total of 2, 4, 6 electrons. Okay, so I've used 6 electrons, so I have 18 electrons left after the bonding has occurred. Now, on step number 4, what we're supposed to do is we are supposed to distribute our electrons to the exterior atoms first. Okay, so oxygen needs 8 electrons to be happy or to have its octet. So we're going to distribute 2, 4, 6 electrons to each one of the exterior atoms. Okay, and the reason why I'm only doing 6 is because each one is bonded to the carbon. So each one of those carbon-oxygen bonds represents 2 electrons. So now I've distributed 6, 12, 18 electrons to the central or to the exterior atoms. Okay, so I now no longer have any electrons to distribute. So now I need to use step number 5 and check if everyone has their octet. Now, if I look around, each of the oxygen atoms has their octet. However, the carbon atom does not have its octet. Because the carbon atom does not have its octet, we must do something in order to facilitate it actually having our octet. Now, since we are out of valence electrons, we're going to have to use a different approach. So, step number 6 indicates that if there aren't enough electrons for everyone to have an octet, then you need to use double or triple bonds. So, in that type of situation, what we will do is we will actually remove 2 of the electrons from the exterior. I'm just going to cross them out, okay? And we're going to share them between the carbon and oxygen atom from which we took that pair. So what we've done here is basically shared an extra pair of electrons so that we stayed within the confines of the 24 electron total that we originally had. So if we go ahead and we check our octet, just like we normally would, we see that each of the oxygen atoms are happy. The carbon atom is happy because it has 2, 4, 6, 8 in each of its bonding pairs. And the oxygen atom from which we shared those electrons is also happy because it has 2, 4 electrons coming from bonding pairs and 2, 4 electrons coming from non-bonding pairs for a total of 8. So all of the atoms in this situation are happy. So now what we must do is we must check our formal charges. So in a very similar way to what we saw on our previous examples, we're going to check the formal charges of each individual atom. Now, in the previous examples that we've done, all of the exterior atoms were bonded in the same way to the central atom. So basically all of the fluorine atoms were equivalent. However, in the example that we have here, we have two sets of uniquely bonded oxygens. So if we take a look here, you notice that this oxygen and this oxygen are both singly bonded to the carbon atom. On the other hand, the oxygen here is double bonded. So that difference in bonding is going to account for a different calculation for the formula charge for this oxygen versus these two. So let's go ahead and let's calculate these. So let's start with the exterior singly bonded oxygens. So let's start with the formal charge. So the formal charge for the singly bonded oxygen, I'm just going to put a line there like that. Okay, so what do we do? First, we find the valence number of valence electrons. So as we've seen earlier, valence electrons for oxygen is 6. Okay, we're going to subtract out the number of unshared valence electrons. So if we look at the electrons here, we have 2, 4, 6 unshared valence electrons. Okay, and then we're going to do half of our bonded electrons, and if we look at that example, we notice that we have one bond. Because we have one bond, that means 2 electrons are being shared. Okay, so that's the number of bonding electrons. Okay, so 6 minus 6 plus half of 2 is going to give us -1. Okay, so because both this oxygen and this oxygen are bonded in the same manner, both of the formal charges will be -1. Okay, notice I'm putting that -1 in those little brackets. Okay, those brackets delineate that that's a formal charge as opposed to a overall charge of the molecule or a oxidation state. So if we go ahead and we continue to do our calculations, so let's do our formal charge for the oxygen with the double bond. Okay, so once again, 6 valence electrons is what we have. We're going to take half of our unshared valence electrons. So if we look at over here on this oxygen, we have 2, 4 unshared valence electrons. So that gives us a total of 4 here. And then half of our unbonded electrons. And in this case, because we have 1, 2 bonds, each bond having 2 electrons, that will give us a total of 4 electrons. So 6 minus 4 plus half of 4 is going to give us 0. So the formal charge on this particular oxygen is 0. And lastly, we need to calculate our formal charge that is associated with the carbon atom. So as we know, carbon has 4 valence electrons. Okay, we're going to have to take the number of unshared valence electrons, and since there are no unshared electrons on the carbon, that number is going to be 0. And then we're going to take half of our bonded electrons. So we have 1, 2, 3, 4 bonds on the carbon. Each bond has 2 electrons, so that gives us a total of 8 electrons. So 4 minus 0 plus half of 8 is going to give us 0. So our formal charge here is 0. So the last thing that we have to, the last two things that we have to do is we have to, first of all, check if our formal charges agree with the overall charge on our molecule. So the overall charge on the carbonate ion is 2 minus. And if we take the sum of all of the formal charges for each of the individual atoms, we see that we get 0 plus 0. Okay, as we can see here, 0 plus 0 plus -1 plus -1, that gives us a total of -2. Okay, and -2 is the original charge of the carbonate ion, so that makes sense. Now, the last thing you have to understand is that whenever you're dealing with ions, okay, whenever your molecule is charged, you must indicate the charge of the molecule by putting a bracket and the subsequent charge of the molecule on the outside. Now, some people will utilize just this kind of shortened little bracket here. Another option, which is completely acceptable as well, is to show the brackets like this. Either way, this answer would be acceptable, and basically this is how you would do the Lewis structure for a molecule like this.